Well, hello there. We are going to launch ourselves into the third major area of the Maths Methods course here today, right now, with review of probability. It's probability. Now, don't cringe. I just saw you, didn't I? Yes, no. This is going to be good fun, okay? So turn your mouth back up again and smile, okay? Put a smile on your dial, because this is great fun. Even though I probably like calculus a bit better, but hey, everyone's different, aren't they? So come on, chin up, let's go. Now, this is easy stuff, okay? We're just reviewing what we already know in the area of probability. So we're going to find the sample space when 3 coins are tossed and the outcomes are noted. Well, look guys, I always love tree diagrams. If I can use a tree diagram, if it's not too horrendously busy and I end up with a morass, I'll always use a tree diagram to help clarify my thinking. So we know for the first coin we can have a head or a tail, don't we? And then for each of those heads or tails of the first coin, we could have a head or tail of the second coin, and similarly for the third coin, for each of those head and tails for the second coin, we could have a head and tail for the third coin, which is a lot of gobbledygook to say, but the tree diagram says it all. That's what we get. Now we can just simply list our sample space. There it is, you see? Follow the tree right along all the branches and the twigs to get to the end result. So now we can write out our sample space is that. Now that funny looking E thing means the universal set, and they always put sets in curly brackets. So that's your sample space. That means everything that there is possible, okay? Well, that was a nice easy little introduction, wasn't it? Yes, Mr. Box, good morning to you, and how are you today? I think he's pretty good. Yes, tree diagrams, they're the best, they really rock, okay? So use them if you can. Question 2. Enrolment records show that at a local school of 800 students, there are 450 females and 350 males, so the girls outnumber the boys. What is the probability that a randomly selected student will be female? Now, they mean that if you took a randomly selected student from anywhere out of that 800 students, what is the probability that that student would be a girl, okay? Well, that means we're choosing from a possible 450 females out of a total of 800 to choose from, okay? And that gets you, if you cancel that down a bit, cancel the trailing zeros, 5 will go into 45 9 times and 80 16 times, so you get 9 out of 16. Nice, easy question. Thanks, Mr. Box. Okay, you get it? Good. Now, look at this. This is a review of what we already know in probability, okay? So we're saying that whatever method is used to determine the probability of an event, the following rules will hold, okay? Now, let's go through them one by one. We know that from the first bullet point there that the probability of any event can only be between 0 and 1 inclusive, yes? For all events which are wholly contained within the universal set, E, epsilon, okay? You get that? Good. Next one. We know that the probability of everything that there is 1, okay? Yes, easy as. Good. Tick that one off. The next one, we know that the probability of the null set, that's that Scandinavian-looking funny thing, means the null set, which is 0, okay? Which means nothing at all. Okay, get that one. The fourth one, we're saying that the probability of not A, see the little dash behind the A? Probability of not A is 1 minus the probability of A. In other words, you can only ever have A or not A, which must add up to 1. A dashed is called the complement of A, or not A is called the complement of A. Yes, now this next one is very, very, very important. That's called the addition rule. That you've really got to know that, okay? Now, in order to explain that formula to you, I'm going to use a Venn diagram. Here comes Mr. Venn. Now, this is really, really pictorial and easy to understand. So when you see it the way I show it to you, I think you'll get it. Okay, the left-hand circle represents A, all events A, and the right-hand circle event represents all events B. Okay, now there is a crossover between them, and so what we have on the left-hand side, just the left-hand side, okay, is the space which is exclusively A. That means A and not B. Get that? The right-hand side we've got B and not A. Okay, that's the exclusively B space. Now in the middle, of course, we've got A and B, don't we? That's the overlapping bit, where they're both happening at once. And of course on the outside we have not A and not B. Okay? Now, I'm shading in A or B. Okay, that U looking thing is an or, okay? Between the A and the B. So that means anywhere in there means you've got either A or B happening, haven't you? Now the way you calculate that is probability of A, which is all of the left-hand side circle, okay? All of the left-hand side circle, plus a probability of B, which is all of the right-hand circle. But hang on, if you do that, you have double counted the middle. You have double counted the middle overlapping section. So, therefore, you think about that, you see? You count that bit twice if you just add the left-hand circle to the right-hand circle. So you have to subtract it. And that's how you get that formula. Yes, Mr. Box, it's a vitally important formula. Okay, that's called the addition rule, and that's where it comes from. Think of the Venn diagram, guys. It will always get you there. Okay, that's that one done. Now, there is a big however here. NB, which is Latin for nota bene, I think. I think that's right. Means note well. Now, if A and B are mutually exclusive, that means there is no overlap between A and B. They are circles well and truly apart from one another. They do not cross over anywhere. That's what you get. That's the little Venn diagram for mutual exclusivity, which means there's no overlap, in which case you've got the probability of A and B, the middle section. Look below that bit where they overlap. Look up again. That bit equals 0 because they don't cross over, they don't overlap. Therefore, the probability of A and B for that situation is just the probability of A plus the probability of B, same formula, minus the probability of A and B, except that A and B is 0. You get it? That's what you get. Okay, thanks, Mr. Box. That's the situation you get for mutual exclusivity. Okay? Happy with that? Good. All right, we'll move on now. Got another example for you. We've got the card game now. We've got one card is chosen from at random from a well-shuffled deck of 52 cards. What is the probability that the card is? Firstly, an ace. Let's do that. Well, we know that there are 4 aces in the deck out of 52 cards, which is 1 out of 13. Easy as, thanks, Mr. Box. Okay, we already know this stuff, so we're just reviewing it, aren't we? Now, not a heart means everything that in the deck except a heart, okay? Well, we know that there are 13 hearts, so therefore we've got, and the rest of them are not hearts, so 3/4 of the deck are not hearts. Very good, excellent. Right, the third one. Now, this one here, either an ace or a heart. Now, I'm going to try and show you this one by using the addition rule because there is some overlap here between having aces and having hearts because it just so happens that one of the aces is a heart. Right. I tried to show you. It's actually easy to work out, but I want to show you using the diagram of the Venn diagram. You've got on the left, you've got the ace circle. On the right, you've got the heart circle. Now, I've tried to represent this as best I could. What I've got in the left-hand circle is the diamonds, clubs, and spades in the exclusively ace department without hearts. Then I've got the ace of hearts in the middle overlap section because it belongs both to aces and to hearts. And then in the right hand exclusively heart section I've got all the rest of the hearts, and in the outside section I've got all of diamonds, clubs and spades except their aces. It's a bit complicated, but however, just bear with me. Therefore I'm saying the probability of an ace or a heart, which is what the question asks, is the probability of aces plus the probability of hearts minus the probability of aces and hearts. Because it just so happens that by counting all the aces and all the hearts, you double count the ace of hearts. That's what I'm saying. That's why you have to remove it at the end, right? So there's the probability of aces is 1 over 13. Yeah, because it's 4 out of 52 aces. Hearts is a quarter of them. Now by adding those two numbers together, you have double counted the ace of hearts. So you have to remove the probability of the ace of hearts, the and bit in the middle of that Venn diagram. You see, that's what I'm trying to say. How that rule works. Hope you got that. Yeah, and then you've just got to fiddle around with the algebra and make everything over 52, and what do you get? 16 out of 52, which happens to be 4 out of 13, because 4 goes into both of those. 4 out of 13, and that's our answer, okay? Thank you, Mr. Box. So do you get how this addition rule works? Yeah, okay, good. Right, now we're moving right along now. Oh, the dentist. Well, that's one of my biggest fears in life, pain and money. So Simone visits the dentist every 6 months for a checkup. The probability that she will need her teeth cleaned, which is a terrible procedure, isn't it, is 0.35, and the probability that she will need a filling is 0.1, and the probability that she will need both is 0.05. I can smell a Venn diagram coming. I like Venn diagrams. What is the probability that she will not have to have her teeth cleaned on a visit, but she will have to have a filling? Okay, look, what I'm going to do for you guys is I'm going to do it both ways. I'm going to do it with a Venn diagram, and then I'm going to do it with what's called a Carnot map, and you can decide which one you like better. I personally like Venn diagrams, but I know other people like Carnot maps, so we'll do both. And part B will be easy to solve once we've got our Venn diagram or our Carnot map drawn. So part A, let's, two systematic methods to choose from, as I've just explained to you. This is the Venn diagram way. We're going to do, then we'll do the Carnot map after that. Yep, okay, so here comes a Venn diagram. Okay, so we've got on the left, we've got the cleaning circle. On the right, we've got the fillings circle. And let's fill in the numbers. We know that. Now, what I do, guys, is I put in the overall first, but there is some overlap here, so we have to make some adjustments. We're saying that the probability of a clean is 0.35, wasn't it? Yes, and the probability of a filling was 0.1. However, guys, the probability that she'll need both is 0.05. So what you do is you put that 0.05 in the overlap bit in the middle, and then you subtract it from each of the left-hand side and the right-hand side, which then adjusts for the fact that you're doing it correctly, so that the whole of the left-hand circle adds up to 0.35 and the whole of the right-hand circle adds up to 0.1. So there you put that in, and then you fix the left-hand side by taking 0.05 off it, and you fix the right-hand side by taking 0.05 off it, which you can see I just magically did with my little eraser and rewriter. Okay, our Venn diagram looks good now, except I haven't put the the outside bit I haven't put in yet. I'll do that in a minute. Now look, that left-hand exclusive circle bit for just clean is the clean and not fill, isn't it? The right-hand side is the fill and not clean. That's the exclusively right-hand bit of the circle with no overlap, is fill and not clean. The middle bit is clean and fill, and the outside bit is not clean and not fill, which is what I think I'd like. However, it doesn't seem to happen very often. So now we'll fill in the outside bit. If you add up those numbers in the circle, they come up to 0.4, and therefore the rest of it, the not clean and not fill, is 0.6. Yeah, right. Now we can answer all their questions now. So what do they want to know? They want to know probability that she will not have her teeth cleaned, but will have a filling. So it's fill and not clean. So you can just look at it straight at the Venn diagram and you can get that is, of course it is, it's 0.05. It's the right-hand exclusive circle bit, the F bit, that has no overlap. It's 0.05. Now, what's part B while we're on a roll here? Yes, thanks, Mr. Box. Part B, what's the probability that she will not need either? Oh, that's the outside bit, that's 0.6. No problem. Great. See how easy it is? It's really, really easy. I love Venn diagrams. I love a picture, guys. But you might like Carnot maps, so here comes the Carnot map version. You draw a 4x4 grid like that. And then you fill in the numbers. Now you've got I've put probability top left, which is what we're dealing with. Then I've got the clean and not clean along the top. And then you've got the fill and not fill along the bottom, along the left-hand side, I mean. And then you put a 1 on the bottom right, because everything adds up to 1 in the extreme right-hand and extreme bottom row. Right-hand column and bottom row, they add up to 1, because the probabilities have to add up to 1. Now we put in the information they gave us, right? Now they told us that the probability of having a clean was 0.35, so I've put that as the total of the clean column. They also told us that the probability of getting a filling was 0.1, so I've filled in the total of the filling row. Okay. Now there was one other bit they gave us, wasn't it? And that was the probability that you'll need both is 0.05. Put that in there. Now we can see what to do, guys. Now the first thing I'll show you is I've filled them in one by one. Look, that number there is 0.30 because the cleaning column has to add up to 0.35, doesn't it? So that necessitates that basically a not clean is 0.30. Yeah. No, that's wrong. I mean a clean and not fill is 0.30. That's what I'm saying. Yeah, it's like a street directory. You read it off like a street directory. They're all ands. Where the rows intersect the columns are ands. So that red thing I've just added there, 0.30, is clean and not fill. Okay, get it? Now, therefore, what can we fill in now? Have a look. You see if you can see something. Okay, good. We can add in that 0.05 as a fill and not clean, because total fill probability has to be 0.1, and we've already got the clean and fill is 0.05, which means the other one must be 0.05 as well, which is fill and not clean. Alright, you're getting the idea? Now you can easily fill in the rest of it now. Think of it, where else can we put a thing? Yes, we can put 0.9 there because the extreme right hand column has to add up to 1. Doesn't it? It does. And also we can put 0.6 in there because we know that not fill column has to add up to 0.9. We're nearly done now. And what's left? I think the bottom row, yeah, 0.65, because we have the whole thing has to add up to 1. So we've got everything we need to know, guys, absolutely everything. So now we can put a tick and we can just answer the questions. Similarly to the Venn diagram. So therefore we can say from the table the probability of a fill and not a clean, look it up now, look it up, what is it? Fill and not clean, do our street directory trick. Yes, match up the column with the row where they intersect, and you got there, and that's 0.05, yeah? Good, Mr. Box, thanks. And we've got B. What do we want to know there? Probability that you will not need either. So you're looking up not clean, not fill. Where is it in the table? Yeah, it's there, which is going to be 0.6. And thank you, Mr. Box, and that's exactly what we got for our Venn diagram approach. So you can work out which one you like better. Okay? But when you do a Carnot map, you've got to do a 4x4. 4x4 and fill it in just the way I showed you, and you won't go wrong. All right. We're going to do conditional probability now. Now, this is really fun stuff. Conditional probability refers to the probability of something when you already know part of the story. You already know part of the story. I'll show you. This is the formula. It says that the probability of A vertical stroke means given that B has already occurred. Okay, that's part of the picture, is the part of the jigsaw puzzle is filled in. describes the conditional probability of an event A occurring when an event B has already occurred, when you know it's occurred. So you say that the probability of A given B is equal to the probability of A and B divided by the probability of B, because you already know that B has occurred. Okay, I'll show you in more detail why that formula is the way it is as we do some more examples. That last line there shows you a slightly transposed version of it, where you've basically multiplied both sides by PRB, and you get the right hand side PRA and B equals the left hand side multiplied by probability of B. Now that's the way I remember it. However, you can choose which way you like to remember that formula, but you do need to remember that formula. Oh yes, you do. Okay, that's called the multiplication rule. So earlier we dealt with the addition rule. That was a probability of A or B. Okay, and this is the multiplication rule, probability of A and B. Okay, now consider the dentist, poor old Simone of the dentist. That's the earlier example. Given that Simone, now did you see that? Given that Simone had her teeth cleaned on a particular visit at the dentist. So we've narrowed the field right down to only those events where she had her teeth cleaned. Okay, what is the probability that she also needed a filling? All right, we're going to. I'm going to show you. This is the visual way, and then we're going to use the formula way. Okay, I like to understand it in terms of both, and so will you. You need to understand a visual approach and just the formula, because they can throw problems at you where sometimes you can use the formula approach easily, sometimes you just have to visualize it because it's just too hard to figure it out any other way. So both you will need to do. You will need to do both. Did you hear that? Yes. Here comes the Venn diagram. Again, here's Simone's dental picture. Okay? Now, alright, now what did they ask us? They said, given that she had her teeth cleaned. Now, that means, guys, if you look at that diagram, the cleaning circle only has a total probability of 0.3 plus 0.05, which means 0.35. So that's all we're dealing with. We already know that occurred. So, really, what it's saying is, it wants to know what is the probability that she had a filling, given that you know that she had a clean. So the filling and clean, okay, is 0.05. That's the middle bit, the overlap bit in the middle between the two circles. Okay? But it's only out of, the total range of possibilities is only out of the clean bit, which is 0.35. Okay? So therefore, yes, that's basically the total range of possibilities. So the probability we're saying is the cleaning and fill bit, because we know that she had a filling and a clean, and it's only out of the total pool here, which is 0.35, the whole left-hand circle. Do you get the idea? That's what conditional probability does. It just narrows the range of what we're dealing with here, okay? It just narrows the field down. So you just divide by the probability of that narrowed field instead of the probability of everything, okay? I hope I've made that clear. So it's 1 over 7. Now, thanks, Mr. Box. Now, we're going to do it with the formula bit now, okay? If we just use the straight formula, we'd say, okay, the probability of a filling, given that it's a clean, looking at the above formula, you can see if you can fill out the rest. See that formula, the first line? It's filling given a clean. Even though they put the given bit first in the sentence, you write it like that. It's a probability of a filling given that she had a clean, okay? That's how you write it in the formula. Now, that's equal to the probability of a filling and a clean over the probability of a clean. Did you get that? Good. Now, we can just read it all off now, okay, and just plug the numbers in, which is going to be 0.05 over 0.35, which is exactly what I was going on about in the left-hand side version with the Venn diagram, and it comes out the same. But that, I hope that I've explained to you the logic of it in the bit on the left-hand side of the page, why it is like that. But then, if you understand it like that, You really, really get it. And that's what I want you to do, to get it. So that when they throw these crazy questions at you, and they give you a bit of information that narrows the field down, you can just say, conditional probability, and launch into action to triumph. Yes, thanks, Mr. Box. 1/7. Good, thank you, Simone. Hope your teeth are good. Now we've got here the school canteen. This is another conditional probability question, which we're going to do visually, okay? Okay, as part of an evaluation of the school canteen, all students in years 10, 11 and 12 at a senior secondary college were asked to rate the canteen as poor, good or excellent. The following results were obtained. Good. Now have a look at that table. Looks like we've got the year levels along the columns and the ratings in the rows, and we've got the numbers of students filled in as they intersect, like a street directory kind of approach, yeah? Good. Now we can see at the bottom right we've got a total of 400 students here. 400 students to choose from, okay? Good. So have you got all that? Alright, good. I've got it. So let's go with the questions now. We've assimilated what they're on about. What is the probability that a student chooses at random, chosen at random? That means 400 students to choose from, guys, from the senior secondary college is in year 12. All right. Okay. You think about that. There's no conditional here in part A. It's just we want to know, we just choose some random from the school playground, and we want to know what's the probability that they would be in year 12. All right, well, how many students are in year 12? Yeah, there's 80. And how many did we choose from? The pool is 400, isn't it? Yeah, 400 there. So basically that is our probability. And we just work it out and we get 1/5. Mr. Box, thanks. That's pretty easy, eh? Yeah, get that? Good. Now, part B for you and me is in year 12 and rates the canteen excellent. Now, there's no givens in there, guys. No givens. They're just saying we're just going to choose a random in the playground or in assembly or somewhere out in the yard when they're all outside. And we're going to say, what is the probability if we just pick a random that they would be two things in year 12 and they have rated the canteen as excellent, right? What do you think? Yeah, I think, you tell me, how many students are there to choose from who basically are in year 12 and rated the canteen as excellent? How many? Come on. Yes, there's 35, that's right. But how many randoms have we got to choose from in the yard? Yes, it's 400, that number there. So now we've got it. No givens there, no givens in sight, so it's not a conditional one. So it looks like it's 5 cancels into both. It's 7 out of 80, okay? Thanks, Mr. Box. All right, now, let's do C. Now, I've just spotted a given, right? They want to know, is in year 12 given that they have rated the canteen as excellent. So now, we've got to work out, we know that this person, so we're narrowing the field down out into the yard. We've collected all the students who have rated the canteen as excellent. So how many would that be? How many? Look at the table. It's 160, isn't it? There's 160 kids rated the canteen as excellent. So that's narrowed the field down. The given has narrowed the field down to 160 students. So therefore, if they're going to be in year 12, okay, well, how many students in that narrowed field are in year 12? Yes, it's a given, and we've got, how many year 12 students have we got? We're choosing from 160 people, but there's only, how many in year 12? There's 35 of them, aren't there? Yes, 35. So therefore, our probability is 35 out of 160. All right? Now we can cancel a Rooney, cancel by 5, we get 7 out of 32. How do you like that? Is that right? Excellent. So that's part C. Do you see what the given does? I'm trying to harp and get it into your mind that the given narrows the field down. It narrows the field down of possibilities. Okay, so you only ever divide by that narrowed field. Okay, that's what you do. All right, I hope you're getting it. Or you can just use the formula. The formula, which I'd rather understand it visually if I could, but sometimes it's just appropriate just to use the formula. So the probability of Year 12, given that they've rated it as excellent, is the probability of Year 12 and excellent over the probability of excellent. Now that is 35 out of 400 for the probability of Year 12 and excellent, and divide that by the probability of excellent is 160 over 400, which just comes to 35 out of 160, which is exactly what we did in the line above. Yes, Mr. Box, thank you. Thank you, Mr. Box. Oh, we're on a roll. Now, what about, we've got to do part D yet. Oh, that's another given. Righto, over the page. Here we go. We're on a roll. We know what to do. Let's read it. We want to know that the probability that they've rated the canteen as excellent, given that they're in Year 12. All right. So I think we've got to narrow the field down to everybody that's in Year 12. How many are there? Look at the table. And we want to know that within that cohort, they rated the canteen as excellent. Okay? It's easy now, isn't it? Yeah, the given information narrows the field down to 80 people. 80 people are in Year 12. Now, how many of those 80 rated the canteen as excellent? Yeah, there's the 80. And how many people? Yeah, 35. So therefore, it's easy now. It's 35 out of 80. 7 over 16. And Mr. Box. Excellent. We've done it. How's your conditional probability thinking going? You're kind of getting it a bit better now rather than just random formulas which they throw at you. There's a great deal of logic and understanding behind it that you need to get before you feel confident with these things, okay? Rather than like lambs to the slaughter in exams when you don't really get it, okay? Here's the formula version. We can just say that the probability of excellent given Year 12 is the probability of excellent and Year 12 over the probability of Year 12. Now, just we can work it out from the table. That's going to be, now the probability of excellent and Year 12 is 35 out of 400, and that's divided by 80 out of 400, which comes to 35 out of 80, which is what we got before, which is 7 out of 16, and thank you, Mr. Box. Okay, there it goes. But I'd much rather understand it visually, as I've been explaining, than just put some random formula in. But you need to know both ways, okay? Let me tell you, you need to know both. Interdependent events. Now, these are very interesting beasts. Now, we know that from earlier that the probability of A and B is equal to the probability of A given B times the probability of B, don't we? Yes, we do. Now, if the probability of A given B is just the probability of A anyway, then it really doesn't matter to A whether B has occurred. It's just going to have the same old probability of A, okay? And that's what you say when A is independent of B. That's what you mean, okay? A doesn't care whether B's happened, doesn't care whether B's coming or going. So that's what you get. That version of the formula I've just written there is the formula for independent events. It comes from the multiplication rule, but it's a variant of it for independence. There it is. Thanks, Mr. Box. It's a very important formula. You need to know that formula too, guys. Yes. So there's 3 formulas you need to know. This one's a variant of the multiplication rule, and you also need to know the addition rule from earlier. That's called the multiplication rule for independent events, yes? Good. Now, what we're going to do now is we're going to work out, what's this? Homework time. Goodness. The probability that Monica remembers to do her homework is 0.7, while the probability that Patrick remembers to do his homework is only 0.4. Okay. If these events are independent, then what is the probability that both will do their homework well? And secondly, that Monica will do her homework and Patrick will forget. Okay, that's easy. We just use the formula. Okay, now, what I'm going to, probability of that Monica and Patrick is equal to the probability of Monica times the probability of Patrick, because they're independent, okay? And that's it. 0.7 times 0.4, which gets you to 0.28, okay? And the probability that Monica and not Patrick is a probability of Monica times a probability of not Patrick. Very easy, eh? And that gets you 0.42. Thanks, Mr. Box. Now, I've drawn some tree diagrams here to show you what's going on. You can always do these with tree diagrams if you didn't quite get that. So the way you draw them is from a single point. You converge out with two branches with the Monica, not Monica. I've started with Monica because they started with her in the question, and I've got a 0.7 on the yes and the 0.3 on the no, not Monica homework. Now, for each of those possibilities, you do the Patricks, okay, and you fill in the bits, and you can see actually, guys, that bit there, the Patricks are really Patrick given Monica on the top. The second one is not Patrick given Monica, because you know that Monica preceded that actual bit of the tree. Do you see what I'm saying? You follow it. That very top one is the probability that Patrick did his homework, given that we know that Monica did. The second one is the probability that Patrick didn't, also given that Monica did, and so on. Do you see that? It's actually quite true. They're givens, those ones. Now, that one there is the probability. Now, they're ands, right? They're ands. That really is a probability that Patrick did his homework and Monica did hers. Ands mean you always multiply the probabilities. You always multiply them. Okay? So, in that case, because they're independent, we just get probability Patrick times probability Monica, which is 0.7 times 0.4, which is 0.28, which is what we got before. But I wanted to show you visually so you can see the tree diagrams work a treat, okay? Similarly for the Monica and not Patrick, it's worked out the same way, okay? That's the one the second part of the question asks that one there. That's that second branch of the final ending up point of the tree diagram, yeah? So that's worked out similarly to what we did above, and it comes to the same thing, yeah? Okay? That's the pictorial way of doing it. You can do it both ways, it doesn't matter. I always love a picture, but sometimes I get so used to them I don't need the picture anymore. Okay? Alright, are you happy? Good. Let's go. All right, now we're doing the dishes now. Now this is a more complicated one, but again, tree diagrams reign supreme for this. So we've got Adrienne, Regan, and Michael are doing the dishes. Since Adrienne is the oldest, she washes the dishes 40% of the time. Regan and Michael are washing them 30% of the time. So when Adrienne does the washing, she has a probability of 0.01 of breaking at least one dish. When Regan does the washing, his probability of breaking more than, at least one dish is 0.02, and then when Michael does the washing, his probability of breakage is 0.03. Their parents don't know who is washing the dishes one particular night. Okay, what is the probability? What is the probability that at least one dish will be broken? I can smell a tree diagram a mile off here. Guys, it's very confusing when you read all these worded questions, but if you can make it into a mathematical, easy diagrammatic picture, it becomes easy. The way I see it here, we've got two things happening. We've got three possibilities of who's washing, and then we've got the possibilities following on from who's washing as to the breakages. So we can represent that in a tree diagram. Okay, yeah, tree diagram. So there we go. That's the first bit of it. That's the Adrienne, Regan and Michael probabilities of washing, and then we put the probabilities of breakage or not breakage on the branches of the tree. Now it becomes a very, very easy matter to work out the compound probabilities of washing and breakage, because that's what they've asked us for, okay? Washing and breakage. So because they're ands, that's, yeah, I'm putting in the appropriate givens there, but they're independent events anyway. So we're going to work out the final probabilities as compound events by multiplying the probabilities together. So probability of breakage and Adrienne is probability of breakage given Adrienne times probability of Adrienne, and that is Okay, it's 0.01 times 0.4, which is 0.004. Similarly, I'm just only picking the breakage ones. That's the Regan breakage situation. Just putting in the numbers. There we go. And then the Michael breakage situation. There. And that comes to that, and which comes to that. Now, if you want to know the total probability of breakage, we could have had Adrienne break the dishes, or you hear that word or Regan could have broken them, or Michael could have broken them. Now, if you've got, it's a cardinal rule in probability that if you hear yourself saying the word and, you multiply the probabilities. If you hear the word or, you add them up. Okay, so with that top line, we knew we had Adrienne washing plus and, in other words, a breakage. So I multiplied those probabilities together. But now I've got to the final situation where I want to know the total probability of breakage. It could have been Adrienne or Regan or Michael. So I add those individual probabilities up. Okay, and that's what I'm going to do. That one, that's Adrienne breaking. That one there is Regan breaking, and that one there is Michael breaking, which gets a total probability of 0.019 of breakages. Alright? Easy as with a tree diagram, isn't it? Now, we can do part B now for you and me. Now, this is a given. Look at this, guys. It's a given. Okay? Given that at least one dish is broken, what's the probability that the person washing was Michael? Here's the pictorial take on it. I know that Michael, I've got a narrowed field here of a total probability from part A of 0.019. That is my narrowed field. So that is the one I'm going to divide by as my total possible probability. Okay? But if given that, we also know that it's Michael that did the breaking. Okay? So within that range of options, we've got a 0.009 there, which is the Michael bit. So the probability of Michael, given that we know breakage occurred, would be Michael's bit over the total range of probabilities we're dealing with, which would be, okay, let's go for it. It's narrowed down to 0.019, as I said, so it's 0.009, the Michael and breaking bit, over the total probability of breaking, and it's that, 9 over 19, right? That's the pictorial way of doing it. So, and I've just tried to show you there the formulaic way of doing it. So that's the probability of Michael and breakage over the probability of breakage, and that's the probability of Michael given breakage, which is what they asked for. Even though they put the given bit in the start of the sentence, we put it at the end of the symbology that we use, the probability of Michael given breakage. All right, you okay? And you're a star. And thank you for listening. That was all of our review of probability. So what do you need to know? You need to know the addition rule, mutual exclusivity with the addition rule. You need to know the multiplication rule, and you also need to know about independent events with the multiplication rule. And you need to be able to draw tree diagrams and think pictorially as well as formulaically in working these things out. And you need practice. So go ahead, have a wonderful time, enjoy your probability, and we'll see you next time. Okay, bye.